Managed to over in front.
You contacted me via text, yes? Or no? Am I remembering right?
You want to go?
No? Me? Yeah,
Oh, no.
okay. All right.
By that like rotates and swing around. Oh, going like goes back and forth. Yeah, so much. Yeah. But I really, we're gonna do. Well, we get one of them. I'm not getting everything, but people. Really on the recommendation. Before you know,
Okay, Maxim, everything that you need to know was recorded and put up in the video that's on the page for the class. If you go in under the 1201 class, go to materials content. And if you scroll down, there's video and support info. And here is the link to the class. That's the video for the entire time that we were in class. I also have been putting up little step-by-step or little kind of blurbs about different topics. And I also included a faculty development presentation that I did earlier this year. So in case anybody's interested in knowing about that. So does that help you out? Okay, good deal. So has everybody managed to get in and work on some of the homework? I know that there was a couple of folks that you had it where you had code lists, you didn't have to go through the process. And then because they reversed that, you were in and now you're not able to get in, so you
Yeah,
have
I
to go.
had that problem, and then, but then I was still able to put in my code.
Yeah,
I
yeah,
still
and-
had it copied.
yeah.
Um,
you were able to go back
Wow.
and just do that process.
Yeah,
So that hopefully, I mean, hopefully next time, hopefully next semester, it will not be something that people have to work real hard at, but you never know. Just so that you know, Maxim, anything that you put into the chat, when I open it up, it's gonna show up on the board as well, so just be mindful of that if you don't want, if you don't want me to do that, just let me know you need to talk to me after the fact. And once I stop recording, then and it's no longer on the screen, then we can have that conversation. Okay. So how did the homework go? Pretty easy peasy? Good? Anybody have any homework problems that they would like to go over that you want to see? You didn't understand what was being asked of you? Okay, that's good. I am all about making certain that you guys are getting what you need. So if at some point, which will probably happen partway through the semester, it starts becoming more challenging and you're like, I don't understand what's going on here. Go ahead and let me know that. If you can let me know it ahead of time, great. If you can't, we'll do it in class. But I will pull up, and do we'll work through the homework problem so that it makes sense to you and we can figure out where things went awry. All right? All right. So we're going to talk a little bit about, well, we've got 4 topics I'm going to try and run through tonight. Those topics are going to be equations and inequalities. We've already dealt some with equations. Inequalities is a little more formal, but there's not a whole lot more there to play with other than how do you tell which side you're shading and whether you need a dashed line or a solid. Okay. We're also going to talk about inverse functions and how to find those. And there's also going to be a bit about composition of functions because those two are very much related. Exponents and radicals and exponential functions and logs. I also wanted to show you guys, and some of you are going to be like, I don't want to learn this, that's okay. But I'm going to show you guys a couple of different ways you can learn how to multiply and multiply quickly. If it comes to a place where it's like, this is too many ways, or I have the way that works for me, that's fine. I'm only trying to give you more tools for the toolbox, right? You don't have to do what I'm saying, as long as you're able to consistently get to the correct solution, right? All right, so equations, we've already talked about the fact that an equation has to have an equal sign. Oh, and those of you that are joining late, I wanted to or not late, but just joining now, I want to make sure you know that if you send me something, and I open it up in the chat, it's going to show up and everybody would be able to see it. So if you need to talk to me about something, feel free to send me a text, or you can just let me know you need to talk to me after and we'll have that discussion. All right. So what happens when we have our equations? Our equations have that equal sign. You have 2 things that are set equal to each other. You have one expression and it's equal to some other expression. Okay. All right. Menu. Well, that's gonna be interesting. Let's see how we,
You probably try to go into the video options.
oh, that's right. Well, that's gonna be.
It'll probably be more like violent for the. But yeah. And go to video setting.
All right, a little better there. Thank you. And I will tell you upfront that as I'm writing, a lot of times I will forget about the fact that I need to move the paper up. If that's happening, if I'm writing and you're not seeing it on the screen, let me know. I'll just move it up. No big deal. Okay? So you've got one expression equal to another expression. Those two things, they are exactly the same. When we say equals, it means they are exactly the same. There's no wiggle room on that. For inequalities, they come in 4 flavors. Okay, the first 2 are less than or equal to. The other 2 are going to be more than or more than or equal to. All right, so these 4 flavors of inequalities. The way I was taught, and this goes way back, but the way I was taught to figure out whether or not something is less than or more than, you're reading left to right, and you need to figure out whether the alligator is going to eat the bigger number, if that makes sense. By the way, I taught that at a school where I had students who were autistic. And at that point, from that point on, I got all kinds of monsters with the greater than or less than symbols in them. All right, so less than, you're reading from left to right, and you're saying this is smaller than this value. And it's strictly less than. It's strictly less than. That means it cannot be equal. All right. If you have more than, whatever expression is on the left is going to be, it's going to face this way. So I have the opening towards the left. Right. So whatever's on the left side of that equation or inequality is going to be more than. And again, that's strictly more than. All right. When we talk about or equal to, we use the same sort of symbol and then we put a line underneath so that in theory, at least, if we do this right, there's your equal sign, right? You've got that extra line underneath letting you know that that is a equal sign. Here I'm going to have same sort of thing like this. All right. Obviously, this is one of those where it's like some of y'all like, we learned this already. Why are we talking about it? We're talking about it because it can get really confusing when we're talking in terms of graphing it. And when you have 2 expressions and you're trying to figure out which side of the whatever do you shade, right? That's why we're going through this. All right. So when I have strictly less than or strictly more than, we have dashed lines. when we have less than or equal to, then we have solid lines. Same with more than or equal to. I'm going to show you a couple of expressions and we'll talk about why some of them are true and why some of them are not true. And they're going to be like, almost feel like the same thing, except there's just enough difference here. All right, so I'm talking strictly less than. Is that a true statement? No, 3 is not less than 3. If I have 3 less than or equal to 3, then I am fine. Right? So keep in mind, this is a little precise. This is a little fussy. Okay, which is why I'm taking a second to talk about this a little bit. All right. When I have more than, same kind of process, right? If I were to say, well, let me go back to the less than for just a second. If I were to say 7 is less than or equal to 3, is that a true statement? No. Right? And it would be false here if it was just strictly less than. Okay. It's really important to keep in mind that you are looking for the precision here. All right. With the less than or equal to, more than or equal to, greater than or equal to. All right. So on this, again, same kind of process. If I were to say I had 3 greater than 3, this one, I mean, we don't have the equals under there, so we're not even going to look at that. In this case, it's a false statement, right? Because we don't have that equals in there. Math does a very poor job of lying. Okay, it doesn't lie well, if you get what I mean. When you go through the process and figure out what's happening, then you wind up saying, oh, this is true or this is not true, right? And it's one or the other. Until you get into quantum mechanics, and we're not going to go there at all, it can't be both. Okay, so it's either going to be one or the other. So if it's incorrect or if it's false, that's all you need to know about it. Okay. So let me take this one step further. If I say on here, I have, I don't know, y equals negative 2x, right? So we're going to have something that comes down like this. It's going to pass through my origin because it doesn't have a y-intercept other than 0. If I were to say less than or equal to, okay, now we had it as an equal, so we know it was a solid line. We knew where we drew the line. Okay, which side of that line do we test? Which side do we shade? Which part is less than? And we're going to pick a number and we're gonna plug it in and see which side, which side we're gonna look at. Which side do we shade? All right. So if I pick the point, 1, 1, and I plug it into that statement right there. So I have a 1 is less than or equal to -2 times 1. That's going to get me 1 is less than or equal to -2. That's a false statement, right? So my 1, 1 is right there. That's a false statement. As soon as you know whether it's true or false, you know which side to shade. If it's false, it's the other side. If it's true, you would shade the side that it would be true for. Okay, if I were to take that, so y is going to equal 1/2 of x. All right, so if I have my x is 2 and I divide it in half, that means my point is going to be there, right? That's that point. If I were to take, it's going to run kind of flat. Let me run that out a little bit. My drawings are off, but the idea is there. All right, so in this case, and that's pretty bad drawing actually. Should have it. Yeah, it went too long. Okay. So I'm going to have, I really messed that one up, didn't I? Okay, so y is going to equal my 1/2 x. So when my x is 2, my y is going to be 1. When my x is 0, well, 1/2 of 0 is still just 0, right? So I've got this. When I get 2, one more, there we go. Still not perfect, but much better. All right, it would actually go through those 2 points. When we have that, and we say it's more than, right? It's more than. We can't use 0, 0. Now, by the way, 0, 0, if it doesn't pass through the origin, 0, 0 is a really nice number to be able to use, right? Because if you do that, and you'll know right away whether it's true or not. Right? It's real. That one is an easy one to pick. If it's not, All right, if it's not 0, 0, you can't pick that one because it passes through the line, or the inequality passes through that 0, 0, that origin. We can't use that. So if I were to say, I want 1, 1, again, I'm going to encourage you to use simple numbers. There's no reason to use 36 or 17, right? The bigger the numbers, the more complicated you make it, the harder it is to figure stuff out. All right, so if I were to say my y is going to be greater than or equal to 1/2 x, well, 1 is greater than or equal to 1/2, right? Because my 1/2 times 1 is going to get me 1/2. So that's a true statement. So that means this point is included in the solution set, right? Here it was not. That was a false statement. Here it is. Okay? Is that making sense to everybody? What's happening there? Okay. All right. Questions on any of that? Yes.
Kind of weird, but yesterday we were doing the numbers, we're talking about complex numbers.
Sure.
Versus real numbers, with real numbers being on the x-axis, complex numbers being the y-axis.
Your imaginary is on the y-axis.
Would that mean that 3i is equal to 3?
It's going to be 3 on your y-axis. Yeah, 3i. When we're talking imaginary, when we get to talking about imaginary numbers, and for right now, we just say, you know, x and y axis, but
Are they like mathematically equivalent to 3i and a 3?
a 3 on the y axis. Yes. Yep. That's exactly it. So 1, 1 is not on the line, which is, yes, that is why I'm using it. Because if it's on the line, it's on the line, right? I can't tell which side I need to change it to, right? Yeah, so you're going to use a coordinate that is not on your line, or that is going to be in the dash line, whether it's solid or dashed. You don't want it to fall on that curve. All right. All right. So, any questions, any further around inequalities? I realize I'm not spending a whole lot of time on it, but I figure you guys have seen it before, right? I don't want to belabor the point. I do want to just clarify some things though. When there may be some homework problems where you're going to be asked to draw in shade, right? And you may need to go in and double check whether you've got a solid line or dashed line when you're setting that curve or that line up. And then you're going to need to figure out which side you shade on. Okay. And it's like that full process is going to happen before you go ahead and submit it. Otherwise it will tell you what's wrong. All right. So if you have, when you get there, if you have any questions, go ahead and just shoot me a text. I've had a couple people already checking in with text, so hopefully that will be useful. All right, so taking a look at inverse functions, and before we go too far, let me pull this up. I went ahead and I put this up in the let's see if I can do this. Zoom is going to work with me here. I want to share. There we go. Come on. No, dude, come on, work with me here. This is one of those cases where every single classroom is set up differently. And we have to figure out the technology in each instance, and it makes me crazy. All right, so that's not the problem. Yes, you would need to do that on both sides, whether it's, you know, less than or greater than, or less than or equal to, and greater than or equal to, okay? So let's see here, why is this not? All right. Why is this not working? Well, no. All right, I'm gonna suggest those of you that are at home, I apologize, this is not behaving the way I would expect. Let's see. If I stop sharing, what happens? There we go. Nothing like having to fight your way through it. All right, can you guys online, can you see the pictures, the memes that are up? I'm not sure if it's allowing the share to happen or not. All right, so you guys can see it. All right, thank you. All right, so this is a case, this is a visual representation of what's happening when you have composition of functions. All right, and we're going to talk about inverse functions here in a moment, but this is a specific kind of ideally inverse function, right? There's multiple ways of approaching it. So you've got, in this first case, you've got a tree and you've got a house. And if you compose them, right, it's called a composition of function. And the notation on that is you've got F with this little circle and G, right, where one is a function of F and one is a function G. Or you can have it F of G of X. All right, so the innermost one or the second one is the one that you start with. Okay, so if I have my tree and my house, if my house function goes inside of the tree, we have a tree house. Okay, is that making sense to folks so far? All right. If I have the tree be the starting place and you put that in to the house, you get the tree growing inside. Okay. So there's a number of these. This is out on under the videos documents, you know, the additional support documents. This is out there already. You can go ahead and look this up. These are actually some really good examples of what's happening. A question might be, when do we ever use this? Well, we use it all the time and we don't even think about it. Okay? If you're making $17 an hour and you're working 36 hours a week, right? You have a function of 17 times your number of hours, right? So that becomes 600 and something. All right. And then when you have that, let's say you're like, okay, well, I know I'm making that much money for the week. How much am I making a year? Right? So now you take what was the answer for the first one and plug it into the function of 52 times that value, because there's 52 weeks in a year. Is that making sense to folks? So we've taken we've put in our X, which is the hours. We get a solution, which is how much we're being paid a week. We take that how much we're being paid a week, and that becomes the new input for how much are we making a year when we multiply that by the 52. So we do this all the time and we don't even think about it. All right. So this is a more formal way, right? Math is real formal and precise. So this is a more formal way of basically saying that same thing. All right. And I have to tell you, there's a couple of them that I think are hilarious. If you have a truck and water, you have a truck with the wraparound or the wrapper on it that makes it look like it's a fish tank, right? And then you have a truck that's in the river. The other one I think is pretty funny is the Friends version. My weird sense of humor. All right, so hopefully, and we can walk through some of these in a moment, but I wanted to set this up so that you guys can see when we're doing inverse functions, we can take our initial input, put it into a function, we put it into the inverse function, and we get our original value back. Okay, that's the point of inverse functions. All right. All right, are you guys now able to see the paper on the doc cam? Okay, thank you. All right, so for an inverse function, you're trying to undo the functions. Right? You have one function, you have an input, you take that output, you put it back into the inverse of that, and you get the original back out of there. Couple of things on the way of notation. Here's your f of x, right? Everybody knows that that's kind of like a y. It's just a little fancier, right? Is everyone cool with that idea? My inverse of that function is going to be f with a -1 up above. Now, I want to be super clear. This is not an exponent. This is saying it's the inverse. Usually you'll see it in parens. Okay, if it's not, it still is probably going to be an inverse, not an exponent. Right? Just the same way this is not a multiplication. My f that depends on x or f of x, that's not multiplication. This is not an exponent either. All right. So if I have an original function of 7x plus 4, and I want to find out what my inverse function for that is, we swap our X and Y. All right, so this Y is now going to become an X, and this X is now going to become a Y. And now we solve so that it's Y equals. All right. So I'm going to have X minus 4 equals 7Y. X minus 4 all divided by 7 is going to equal Y. This is my inverse function for this. Making sense? By the way, is that big enough, or should I like close that chat? You guys can see it okay? All right. All right. So let me go through, I'll do a couple quick composition of functions. And we'll get started on exponents and radicals after that. All right. So composition of function. By the way, I want to just emphasize that this works both directions. And the reason it's important that I tell you that is because at some point here, very shortly, we're going to find out that it doesn't always work both directions. Okay, so if this were my function, that's going to become my F with that little -1 up there, right? So that's going to become my inverse function. All right, that doesn't matter when we're talking inverse functions, doesn't matter which way we go. If one formula is going to be the function, and then the inverse of that, if you were to start with the other one, you start with what was the inverse and go back the other way, you'd still have, they still undo each other. All right, and I'm actually going to show you that happening here, but I'm not going to do both versions of it. I do want to make sure though that you guys know that that's true. It's a little mind-bending because up until this point, I don't know that does anybody, or have you encountered places where if you multiply things in different orders, it doesn't give you the same answer yet? No, this is, it's called matrices. And matrices, if you have an A matrix and a B matrix, you multiply them together, you get an answer. If you have a B matrix and an A matrix, you get a different answer. And that's a little mind-bending, because we're not used to that when it comes to math. We're used to, it doesn't matter which one starts. All right, so let's go ahead. I'm going to start with my X minus 4 over 7. All right, and now I'm going to plug this into this function. All right, so this is my input into the second one. So instead of having a 7x, I'm going to have an x minus 4 all over 7 plus 4. Okay, are folks seeing what happened there? If you're not seeing it, let me know, because this gets, I will tell you it's confusing until you get it. This is one of those cases where math is hard until it's easy. You'll hear me say that a lot too. All right, So if I go ahead and plug that in, right? I have a 7 over 1. And this thing here, I've got my x minus 4 all over 7. Those 7s can cancel out. Right? And then from there, I have my x minus 4, and got those in parentheses. I can't do anything with them while they're in parentheses at this point because it's a variable. So I take those parentheses off. Take the parentheses off, don't add them back. Okay, so that's how you know that that is actually inverse function. Those two are inverse functions of one another. I can put in my x. I run through one. I run through the next one, and it gives me my x back out. All right, so let me go ahead and do composition of functions, a little more on that. If I have, all right, I'm going to have you guys help me out. Think about two different functions. Somebody give me one function, not terribly difficult, but you know, a slope and a, yeah.
3x minus 4.
3x minus 4. All right, what's another one? 2x plus 3. All right, this is going to be one of those cases where the order you put them in is going to give you two different answers. Okay, so if I have f composed with g, and that is exactly the same thing as f of g of x. All right. The one, we start with the innermost first, or we start with the last one and work our way back. All right. I'm literally gonna write this out. I've got my g. All right, that's gonna be my 2x plus 3. And then I'm putting that into this function. So I have a 3. This is my x here. This x has been replaced by this. Okay. So when you do that arithmetic, I come up to 6x minus 5. I'm going to do the other way around now. Somebody's looking at it like I made a mistake. Pardon?
I think you said 6x minus 5.
Oh, plus 5. My bad. If I said it, okay. If I said it, I told you negatives were going to be the bane of my existence, right? Y'all knew that. All right. So let me go ahead and go the other way around, right? So now my f is going to be the innermost, and we're going to have the g be on the outside, right? So my g of f of x, right? And I want to write those in both forms because you can see them in both forms. They are exactly the same thing. Personally, I like this way because it tells me exactly what I'm doing, right? But this is g composed with f, and this is g of f of x. Personally, like I say, I like this one better just because it tells me precisely what it is we're doing as opposed to, oh yeah, that circle, I know I have to do this, and which one do I do first, right? All right, so my f of x is going to be a 3x minus 4. And now this is going to get plugged into this g of x. All right, so I have a 2, and this x is now this thing, right? Is that f of x. And while they're very similar, you've got the 6x plus 5 on the first one, you've got the 6x minus 5 on the second one. Those are two different numbers. And we could have gotten more creative and done other things. We didn't, but that's okay, right? So I want to make sure folks realize, though, that the composition of functions is going to matter which way you do it. Okay. And if you ever kind of in doubt, go ahead and hop into the class under the videos and supporting documents, and then I have it composition of functions, and I have those pictures all sorted out for you, those memes. All right. How you guys doing? Need a little break, or are you good? We're good? Okay. So now we're going to talk about exponents and radicals and some of the rules around those. And I want to emphasize something here that I don't know very many instructors who emphasize it. And I think it's important that we do, because it helps make things make more sense. If I have x times x times x, we're all cool with the idea that that's x to the third power, right? If I have a square root with that x underneath, that's also an exponent. That can be rewritten as x to the 1/2. Right? If you stop and think about it, it makes sense. If I have x squared under the square root, I get x back out of there. In this case, I could also have written this as x squared raised to the 1/2 power, which is going to give you x2 over 2, which is just plain x. Okay. So let me kind of run through some of the rules around exponents and radicals. And like I said, I know that a lot of you have seen a lot of this stuff before, so I'm trying to get through a whole bunch of it at the beginning, so we have that time for when things start getting a little like, I've never seen this before and this is kind of weird, right? And you have to take a little more time to think about it. All right. So if I have x to the 5th times x to the 7th, that's going to become x to the 12th. Be careful. A lot of times when we look at that, we want to multiply it. Okay? Effectively, what's happening here? Right? This is the same thing as this. This is the same thing as this. Right? When I go ahead and add them up, right? I've got x times x times x. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 x's multiplying themselves. right? They're multiplying themselves. So that's where we get that x raised to the 12th power. What happens if we had x to the 8th over x to the 4th? Right? If I were to write these all out, I can cancel this one and this one, this one, and this one, and I'm left with x to the 4th. All right. What we can do from here, instead of leaving it like this, we can recognize that this is going to be subtracted, right? That if we have a negative exponent, it's in the wrong part of the fraction. Okay, and that's kind of the way I think about it. So if I have x to the 8th, and then I have x to the negative 4th, right? Now it's the same as doing this step, right? It's not nearly as challenging. X to the 5th because I had it to the 8th. Yeah, okay. All right. Yes. All right. If we have, I'm going to use a different letter here. If I have m raised to the 3rd power, and then I square that, now I've got something that's doing this. All right. When I raise the power to a power, my exponents multiply. When I was just multiplying two different terms with exponents on them, right? That's just going to become an addition. And that it starts feeling weird because now all of a sudden we're playing with addition and multiplication. And now we're talking about raising a power to a power, and we're actually multiplying, right? It feels a little weird to do that. I get that it's going to feel weird. Okay. I promise you it's true. And hopefully my writing it out will convince you of that. All right. So I've already talked about a square root being 1/2. If I have any number other than just blank there, right? It's understood that that's the 3rd root, the 4th root, however many, right? That number there tells me how many of those I have to have under that radical to have 1. Okay. So in this case, I have x to the 1/3 power. If I have, and I'll show you on the calculator, you have this as an option, by the way. You can do your
square root, which is kind of a freebie, and then you can select what root you want to take on your calculator, which is kind of cool. All right, so if I have a fourth root of x to the 7th, all right, I'm going to say that this is exactly the same as that, right? I've spelled it out. I'm making it so that it's visible, hopefully, for everybody to see. All right, at this point, this fourth root, I need 4 of them to make it become 1x. Okay? So here, there's 4 of them. So I have an x times a fourth root with an x to the 3rd. I can't just drop off what's left. Okay, I have to account for that. I could also write it as x times x to the 3/4. All right, because that 3 is underneath that square root, and that 4 becomes the denominator for my fraction. Yes. You can. There's no reason why you can't have an improper fraction.
But, you could then take it to be like x to the 7/4 is equal to, x to the power of 4/4 times x. To the
Yes.
power of 4, and
Yep.
just have it be x.
Yeah, that's exactly right. So, I mean, it kind of becomes what's your comfort level, right? There are going to be times when you're doing the homework, it's going to make sense to like take it all the way down to mixed number as opposed to improper fraction. Other times it may make sense to leave it as it was, right? So this is just fine. This is just fine. You could also say x to the 7/4, and that works too. Right, and I think what you were, tell me if I'm right on this. You were saying I can split that apart to be x to the 4/4, and then x to the 3/4. Right, yeah, that's absolutely correct. Okay, so when you have a value that's even, whether it's 2, like for our square root, or 4, or whatever, if you have something that's negative under that value, it is no longer a real number. Okay? I want to make certain that we're clear on that. So if I have if I have 3, if I have a -3 under a square root, and I know we're going to talk more about imaginary numbers a little further down the road. I want to just make certain though that folks are aware of this. If it's an odd number, like if you had a 3, I'll show you here in a second. If you had a 3, a third root, right, a cube root, you could wind up with it being a regular number as opposed to being something imaginary. So in this case, I'm going to pull this apart just a little bit. If it's under the radical like this, you can pull it apart, right? You can factor it apart. And sometimes that's really useful. All right. So my square root of -1 is going to get me I. So this is I. So my answer here becomes 3I. Yes, you're right. Yep. if I have the cube root of -8, is there a number that when I multiply it by itself 3 times, I wind up with a -8? Yes, there is. There we go. That only works. That's only going to happen when you have an odd number like that. Right? When you have a denominator that's going to be an odd number, or you're talking about an odd number root. Right? So 3, 5, 7. We're good with that? Okay. Seven, 3, okay. It's the second. Under the square root, it's 3 times -1. Okay, that -1 becomes an I. Okay, cool. Okay. How are we doing for time? We're actually doing pretty good. I want to hand out some I'm going to show you some of the methods of multiplication, just because we're going to go from exponents and radicals, and then we're going to do exponential functions and logs. And I want to make certain that we have a little bit of a breathing space in between there, so that hopefully we can make it, you know, be separate. Some of you may already know some of these methods, and that's fine. Like I said, I want to make sure that folks know how to do this stuff. Okay. And I need to get you one. Sorry, and I had almost the right number. All right. So on this one, these are forms of multiplication. The lattice multiplication, I know that they are teaching it now on a more regular basis in the middle schools and high schools. The old-fashioned way was pretty brutal. You had to line everything up, and you had to keep track of, you know, carrying that number, carrying the tens place. This is a whole lot cleaner as far as that. Okay. So let's get a 4-digit number times a 3-digit number. Someone give me some numbers. I'm sorry. That's too easy. 10, something else. 75. All right. Other numbers, 3 numbers. Come on, guys, be brave. 8. What was it? No, it's got to be an integer. Keep it as an integer. Sorry. I'm being mean here. I mean, 6 and 7. All right. So this is actually really nice if you're trying to get a bunch of stuff done, right? Everything in this 0 column is just going to be zeros. So 0 10s and 0 1s all the way down that column. Here my 1s, that's also going to be very straightforward, which is one of the reasons why I made us change some numbers. Okay, so I have a 0 8, I have 0 10s and an 8 1s. right? My numerator, the thing that goes in the upper part of that triangle or that square, that upper triangle is going to be my tens place. The lower one is going to be my ones place. All right. And if you notice, it doesn't matter where I start doing this multiplication, right? I can kind of do it in any order I want. So 7 times 8, I'm going to have a 56. 5 times 8 is going to get me 40. 7 times 6 is 42. 7 times 7 is 49. 5 times 6 is 30. And 5 times 7 is going to be a 35. Okay, we're all good with all of that? Is everyone seeing where those numbers are coming from? My tens are in the upper part of that square. My ones are in the lower part of that square. Now we're going to add along the diagonal. Here I have a 5. 0 plus 3 plus 9, that's going to get me a 12. So I'm going to have a 2 and a plus 1. All right. So 0 plus 3 plus 2 is going to give me 5. That's going to get me 9, 10. So that's going to be a 0 and a plus 1. $10, $14, $15, $22. Right? There's my 2. And there's my plus 2 for the 20. $5,006, that's going to get me 11 plus 2, that's going to get me 13. And 0, 8, 0, and 1 is going to get me 9. I don't know about you, but that's a whole lot faster than if I had to do it the long way, right? The old fashioned way.
That's multiplying all those.
Mhm.
together.
Yeah. If I were to multiply this 1,075 by 867, 932,025 is my answer. It's kind of trippy when you stop and think about it. That's pretty cool.
I think that's pretty close to how a calculator does.
Probably. But as I say, this is actually, I had my very first teaching year, I had a class where I was trying to show them this and they were like, oh, that's way too much. That's doing too much. I'm like, I can go faster than you can put it in the calculator. I said, the only thing I'm going to ask is that you let me set up the grid ahead of time. And they were like, oh yeah. And they were making fun of the fact. And I actually beat them with them trying to put it into the calculator. Yeah. So it is actually, it's pretty fast, right? If you wanted something to happen quickly or be able to look at it quickly, that is a method for multiplication that will help you out. I'm going to show you another 2-way. I warned y'all, I make mistakes. You're welcome to like call me on them. All right, so let me go back through the partial products because I dropped off some tens places. This is what we would have had, our 7 times 8, 30 times 8, 50 times 7, and 30 times 50. Okay. All right. I'll let y'all update your information. All right, so the other way around. You've got the 40 times 60. And then we start subtracting the pieces that are too big, and then we have to pick up the last piece that we took out too much. So the 3 comes from the 37 to the 40. And then the 2 comes from 58 to 60. So we have a 3 times 60, a 2 times 40. And then we have to add back the little piece that we took out from both of those. And that also gets us to that 2,146. All right. So let's see. Oh, we had a place where. Did I take that away? That. All right. So let's talk about exponential functions and logs. We do a whole lot with base 10. Did I tell you guys about base 60, where that comes from? Okay, I won't bore you with it again. I thought it was really interesting that that's where it came from. So we have an exponential function, and trying to think of a good one. So if I say I have a base, let me do the abstract, and then I'll go ahead and we'll take it from the abstract and put it back into some actual numbers there. All right. So you start off with a base, right? That is a number that is multiplying itself however many times, right? That exponent is what's telling us how many times we're multiplying that base by, right? I'm hoping that everyone's real clear on the fact that you're not multiplying your base times the exponent. It's the base multiplying itself that many times. And that gets you a result. When you're talking in terms of logs, all right, we have a log base and then we have our result, and we're trying to figure out what our exponent was. All right. The base that you have here is the same base here. Okay. I will also mention that there's two types of kind of default ones that we go to. There's our log, where we don't put a number, where we don't give a base. That's understood to be log base 10. Okay. If I have what's called the natural log, or LN, and I want to emphasize that that's LN, because I've seen a lot of people try to put IN, and when you're trying to put that into your answers in Pearson, it will tell you it's wrong every single time, because you're not giving it the LN, right? So I want to make sure everybody's clear on that. That's an LN. That's the same as log base E. And does everybody know about E? Or just, is that, okay. A couple folks are not 100% sure on. Okay, so, all right, sorry, I didn't catch this comment. Will we use the way we did our work with the rounding problem? So you can use whichever way. No, you are not required to get the hang of it. This is another way to do it. Okay. All right. Yeah, whatever works best. Yep. It helps if I don't confuse myself first. All right. So E is a number that gives the idealized compounding or growth or decay factor. Okay, it's a number like 2.71817, and it goes on. It's like pi in that it's irrational. It goes on forever. It's used everywhere in finance. Anytime you're talking about compounding interest, E is involved. Okay, anytime you're talking about growth of a population, E is involved. Right, so biology, all of that gets, E comes into it. Okay, so these are the two that are kind of defaults that we go to. Those two, we do not need to detail what our base is. They're understood. Okay, every other one we need to address. So if I had, and I'm going to go with some really easy ones to start, but if I had 10 raised to the third power, right? There's my 10 is my base. My exponent is 3. My result is going to be 1,000. If I wanted to go the other direction where I'm taking a log, I would say log, and because it's a base 10, I don't have to put the 10 there. All right. This gets to be very helpful when you're talking in terms of scientific notation, right? Taking logs. We can go from stuff that we can only see with electron microscopes to entire galaxies. And I think it's only like 40 between, which is pretty extraordinary. Okay, so is this kind of making sense what's happening here? This is my exponential, and here's the log showing how that relationship. Okay. So if I were to say log base 3, 81, what's going to be my answer? Well, 81 is 4. Yes. So 81 is 9 times 9, which is 3 squared on each of those. So, yes. All right, so that is a way of addressing our, addressing multiple different bases. And I'm gonna say, I think the worst that we get to is 4, the base of 4. Okay? So it's going to be helpful to kind of know this stuff though, because there comes a point where we're going to have to break things down and figure out what's going on. We're going to wind up solving for our values. Here you've got so log base 2, 32. 2, 4, 8, 16, 32. Right? So my exponent on that is going to be 2 raised to the 5th. Right? You should be able to interchange, go back and forth between those. Okay? Okay. Couple things that you need to know. These are kind of like always kind of deals. If I have a log, whatever my base is, and it's 1, my exponent on that is 0. If you'd like, I can show you why. If I have a base of 2, right? 2 over 2. So that's 2 to the 1 minus 1 equals 1, right? So this becomes 2 to the 0. Is everyone seeing that? Does everybody know that anything except 0 raised to the 0 power is 1? Everyone solid on that? Okay. So my log base, whatever it is, as long as it's not 0. By the way, there are people who try to write whole PhDs around whether 0 can be raised to the 0 power, whether you get 1, whether you get negative infinity, whether you get, sure, absolutely. Just give me a second. There are people who are writing their PhDs, whether 0 raised to the 0 power is going to give you positive infinity, negative infinity, 0 or 1. And that's like math way beyond what even I want to bother with. So I would say that don't stress about it, but it's kind of, it's interesting to know that there are people who think way too hard about 0. All right, so the question was, can I explain one more time what I did? What is the 2 in the numerator position? Okay, so I was using the 2 to try to help me show something raised to the 0 power. Okay. So I have, it could be any number, but anytime I have a number, if I have 12 and I raise it, or if I am dividing it by 12, right? I can rewrite this as being 12 to the first power times 12 to the -1 power, which is the same as 12 to the 0 power, which is 1, right? And all of this feels like it's extraneous, right? You know, if we have 12 over 12, we know that's a 1, right? But like I said, sometimes you have to kind of jump through the hoops to kind of convince yourself of some of this stuff. Bless you. All right, does that help you? Okay, super. All right. If you have a log base 8, your exponent on that is going to be a 1. Anytime you have a number raised to the exponent 1, you have the original number back. Right? That's true, again, in every case except 0. All right. So sometimes it feels like it would be easier to break stuff down, right? So if I have, say, a log, and I'm going to say 1 million. All right, that's a fairly large number, and it's just assuming that you're uncomfortable with large numbers. A lot of people are, believe it or not. And that is pretty common, actually. It's like the bigger it is, the more intimidating it seems, right? Or the more complicated something is, the more intimidating it seems. Okay, so here I'm going to pull this apart. So I'm going to say log, again, my base 10, and I'm going to say 1,000 times 1,000, right? Because 1 million is 1,000, 1,000. So I've got this multiplication happening here. And this will make more sense when we start dealing with variables in there as well. But I want to make sure that folks can kind of see the reasoning behind this. So I'm multiplying, but I can go ahead and say log of 1,000 plus log of 1,000. It feels weird because we're starting off with something where we're multiplying, and then we're shifting it to addition, right? This is where it starts getting a little bendy, right? The stuff that we already have, kind of feel like we always have known. Some of the rules are starting to get a little bendy here. All right, so if I can do that, and let me spell that out. So it's going to be log base, and I have an m times n, whatever those two numbers are, as long as we're not talking zeros, right? Is it okay if I just, we assume that the zeros are not going to be included in that, so I don't have to keep saying it every time? Okay. So that's going to give me a log base b of m plus my log base b of n. Why is it equal to 3 plus 3? Okay, well, if I have, good question. If I have a log base 10 and I have a 1,000 out of the deal, what was my exponent to take 10 to 1,000? Right? I have a 10, 100, 1,000. That's going to be a 3. And because I took that, is that making sense now? Okay, cool. So that's how this one happened. Same thing with the next one, which is why we can say, oh, that's actually going to be a 6, right? And if you had taken the million, you would have been able to do that the same way. All right. If I can do the multiplication like that and I wind up adding, what happens if I wind up dividing? What do you think is going to happen? We're going to be subtracting. Okay, I'm going to make a point of clarification here in just a moment, but I want to make sure that I get this all written out. So it's going to be log base B, not B, times M, and it's going to be subtraction of log base B, N. All right. I want to be super, super clear on this. This is not the same as this. Those are two different things. They're not equal. Right? They are not equal to each other. So just be mindful of that. It's real easy to want to get yourself tripped up that way. All right, we have a few more rules. If I have a power on my whatever, right? So if I have log base B, M raised to the N power, I can pull this out front. Okay. All right. So if I have, let's say I have two weird bases. I have a base of 3, right? And I want to get it into something I can use, or I have a weird base, and I want to get it into something I can use. All right. There's what's called change of base. All right. And our formula for that is going to be we have log base B M, and that's going to become log M over log B. Now, I want to point out that this is not saying log base B, this is saying log base 10. You can also do it with ln, okay, the natural log. But if you pick one to be base 10, the other one also has to be base 10. You can't switch them up. Okay, so I'm gonna say this is technically base 10, and I'm gonna put that on there just so that it's clarifying that it's base 10. I could also have said ln of m over ln of b. All right, so log of, let's see here. If I have a log, let's say I have a base, and I'm gonna go log base b, and I have an x. Right, so this is an exponent. Right, this piece is an exponent. My log base b and my b undo each other, which leaves me x. Okay, just to clarify that a log m over n equals no on the last page. Okay. This one? This last one? Okay, so I have log base b. And then I have an m over n. All right, so I've got I've got a number dividing. All right. So I've got my log base b, m, and then I'm subtracting my log base b, n. So it's not log m, okay? Is that a little better? Okay. Cool. So if I have a log base b raised to the b base x, I'm also going to have an x.
Is that log base b, is there any, integer there? Or log base b of 10 to the power of b over x?
Log base, let me think here for a second.
Is it log base?
I'm raising, okay, so it's log base b, right? And then I'm raising it to the b. I think it was like this.
Is that
So it's
like log base b of 1 to the power?
log base b,
Of b to the power of x.
b to the power of x.
Okay, so it's log
Right.
base b of b.
Yep. So yeah, sorry, it's a little log base b to the x is also, I mean, this is basically the reciprocal of what we just did.
Yeah.
Okay.
I don't know if it was a b sub x.
Yeah, no, and that's okay. I mean, my handwriting was messy on that. And it's just fine to call me on that. All right. So. Questions?
And number. They're the same, it's always been cancel out.
Yeah, you have a log base b, and then you have the number b raised to some power, right? If you stop and think about it, this is my base b here, and this base, right? We said that those are gonna cancel each other out, it's gonna become 1.
Yeah.
So it's 1 raised to the x, right? Does that make sense?
Yeah.
Okay, All right. So questions? Going once? Questions going twice? All right, love you, bye.
Yesterday,
Okay,
I still can't log in.
okay,
Okay.
okay.